Sure. Hello, everyone. My name is McCoy. I'm a third-year PhD student advised by Vikash Mansinghka at MIT's probabilistic computing project. Today, I'll be presenting preliminary work performed with my collaborators Mathieu, Huot, and Alex Lev on building a reverse mode for a new ADEV algorithm called automatic differentiation of expected values, or ADEV. Now, automatic differentiation is the fundamental technology behind the deep learning revolution. And on this timeline of deep learning, one thing you'll notice is that the fundamental algorithms for AD were developed in the 1950s and 1980s, and it took 30 years for deep learning to mature to the point where practitioners began to construct interesting programs. Around 2015, industry takes notice, and then you start to see the emergence of industrial-strength AD automation frameworks like PyTorch and TensorFlow, which provide abstractions designed to build neural networks on top of AD implementations and put the resulting programs on GPUs. Now, the success of this AI paradigm relies on the fact that these frameworks do indeed cover a broad space of possible programs and their derivatives. Out of the box, these frameworks typically expose program transformations or infrastructure which take real-valued functions P to their gradient programs. Sorry. Combined with the necessary elbow grease, this automation has been sufficient to produce some really interesting programs, including the programs behind AI technologies like ChatGPT, Stable Diffusion, and Llama. But the big caveat with the automation provided by these frameworks is that the operations allowed inside P, which the automation will correctly handle, is restricted. In other words, there are programs which aren't handled out of the box. For instance, when programs contain probabilistic effects, these frameworks will ignore them and silently compute incorrect gradients under expected value semantics. Here's an analytic example just to make the point. For this program, we can compute the expectation exactly and take its derivative against naively applying an AD operator and taking the expectation, which will produce the wrong thing. So there are programs which these frameworks fail to provide AD automation for. We'll be focusing on programs which include sampling and expectations, where the expectation is taken over a distribution which depends on the parameters of interest. This is a broad class of possible objective functions, including variational inference, reinforcement learning, essentially any setting where a stochastic system needs to be controlled. How do we automate the setting? If we step back, the things that we want to automate fall out of the equation for unbiased estimators of the gradient. We want to be able to automate the construction of a probabilistic program Q whose expected value over its denotation satisfies the equation. Here's an example program. Note that while this program just defines a sampler over its return value, we are thinking about the expected value of the denotation of this program, which is the argument of the differentiation operator on the left-hand side of the equation. But it's a program, it's a structured object. We want to come up with some sequence of steps to reduce a Q. How do we proceed? The strategy that an expert would use would be to cut the program into pieces. The key observation behind this strategy is to utilize a decomposition in terms of conditional expectation, meaning we first think about the expectation of C1 over B1 and choose a gradient estimation strategy for that. Now, there's a variety of these estimation strategies, even for discrete random variables. We could choose to use the score function reinforce estimator or the measure value derivative estimator. We could even choose to enumerate exactly in this case. Now let's say that we choose to use the reinforced estimator, which I'm showing on the bottom right. The next step is to write this strategy into code. But note that during the application of this strategy, we recursively apply nabla, here to C1 and to the log probability function of the measure P. The gradient with respect to the log probability is not an issue here. We can handle that with deterministic automation. But note that C1 involves sampling as well. Here, this implies that we must also choose a gradient strategy to handle the nabla C1 terms inside the reinforced strategy for B1. Now, of course, we could also use reinforce for this term, and another nice thing to notice is that at this stage, C2 is deterministic, meaning it doesn't involve sampling. So when we apply nabla, we can rely on automation for derivatives of deterministic functions. And just to show that all laid out, here's the Q program, which computes the gradient estimator for our original program with the two reinforced strategies applied. I've added the score function correction terms for each branch. Now, it should be obvious that this won't be easy to do manually for more complicated programs. I've checked this over a few times, and I'm relatively confident that I haven't made a mistake, but it's easy to make one. And if I want to change the estimation strategies I used, I have to repeat this process all over again. And the example here is not just for pedagogy. This program pattern with the flips does occur in practice. In real machine learning models like the one I'm showing on this slide, a deep generative model of multi-object images called attend, infer, repeat. Now, for the process I've just walked through, there is robust automation. In particular, an algorithm called ADEV from last year's POPL provides automation exactly for the process which we followed. ADEV presents a differentiation transformation which automates the construction of unbiased gradient estimators for programs via an extension to forward mode AD, allowing us to derive a Q program for gradient estimators. It also includes language automation and sampling primitives that hold gradient strategies, so changing strategies to derive new estimators is a small change to existing code. But critically, the automation relies on forward mode AD. And while forward mode AD has historically been easier to reason about, it has known scaling issues. So that prevents usage of ADEV in settings where we have a large number of parameters. If we return to our example, this is roughly what ADEV's forward mode would produce. It's automated a lot of the tricky details for us, including the application of the estimator strategies, and it works by propagating dual numbers through the code. Here, P1, T1 is the dual for P1, and P2, T2 is the dual for P2. But notice that, as is true in normal forward mode, to compute an estimate for the gradient vector for P1 and P2, we need to invoke our program twice. This is the well-known scaling law for forward mode. For scalar functions, the number of invocations required to compute full gradient vectors goes like n, where n is the number of input dimensions. This directly implies that for even modest deep learning architectures, examples like the one I presented earlier are out of the question. So clearly, we'd like a reverse mode. We'd avoid the scaling issue, and we could provide ADEV automation for settings such as this one. Now, ADEV gives us the left-hand side, the implementation of a forward mode estimator. We really want a type of transformation which allows us to go to the right-hand side, to a reverse mode implementation. Our solution is to consider a piece of work by Radul et al. On automatically deriving a reverse mode from a forward mode. In their language setting, they study J, the normal forward mode AD transformation, U, a transformation which unzips the nonlinear and linear parts of a computation, and T, the transposition of the linear part. The key observation from their paper is that reverse mode is a composition of these transformations on their language. Our contribution is to notice that if we study a version of the language presented in ADEV, a restricted version, a version of the language which is restricted to Radul et al.'s linear A sublanguage, we can replace the J transformation with a slightly modified version of ADEV's forward mode, a version which eliminates higher order functions in the target language of ADEV, and this will satisfy the first order requirements of YOLO's linear A language. We can then apply the unzip and transposition transformations to derive a gradient estimator. If we return to our previous example, I'm going to walk through the sequence of transformations symbolically. First, for a program P written in the restricted version of ADEV's language, we apply forward mode AD to construct the program on the right-hand side. And while we're still working on the formal presentation of this part, our proposition is that the result Q can be soundly assumed to lie within the domain of the unzipped transformation from YOLO, the U transformation. When we apply the transformation, we get two parts. The nonlinear part requires the primals, and it includes something which is new to YOLO from our setting, any sampling primitives that are used in the Q program, as well as the subparts of the computation which don't depend on the tangents. It also returns nonlinear intermediates. And these intermediates are required by the linear part along with the tangent perturbation to compute the linear perturbation to the function. Now, after applying U, the recipe from YOLO is to apply transposition to the linear part, from which we construct a gradient estimator by utilizing the nonlinear and transposed linear parts, as is done in YOLO. Thank you. Now, our proposition is that the resulting gradient estimator satisfies the unbiased estimator relationship we discussed at the beginning of the talk, and as is true in reverse mode, doesn't require repeated evaluations to construct the full gradient. In other words, the composition of the two techniques take our original program directly to a reverse mode estimator. Now we have some preliminary empirical results. We tested our automation by implementing ADEV and JAX and applying the YOLO transformations to the estimator programs which result from ADEV's forward mode differentiation transformation. The result of our experiments is that we successfully trained variational autoencoders with efficiency that rivals the best-in-class industry automation for variational inference. At the same time, we expect our approach to readily scale to more complex expected value loss problems by virtue of ADEV's compositionality and modularity. And to conclude a high-level overview of our proposed automation, we inherit the beneficial properties of ADEV, including correct by construction gradient estimation for expected value loss functions and the ability to easily change estimation strategies. But in addition, our reverse mode implementation allows ADEV to derive efficient gradient estimators for problems where the program L used in the loss has a high input dimension to small output dimension, and includes sampling and expectation, as is covered in ADEV. In addition, for the restricted language that we studied, which is practically equivalent to JAX's subset of Python, our transformation is compile time only, meaning there's no extra runtime cost induced by our transformation. And finally, just a final shout out to Tom Smeding, who helped prototype a variant of this approach using his work on dual numbers reverse AD with our group last year. Thank you, that's it.